next speaker is Wolfgang Kall from McMaster University. He will tell you a little bit about, or a lot about the unbundling data.
Thank you for the introduction, and thank you all for being here. This is mainly work of my PhD student, Al-hassy, that I'm co-supervising.
I think the mic might not be working.
This is actually mainly work of my PhD student, Al-hassy, that I'm co-supervising with Jacques Carrette. So he's worked on this language feature to unbundle data at will, and I'm not sure whether that really tells you what it's about. It's essentially one take on more extending module systems to make them more powerful. I'll use the kind of examples that we are using and the kind of languages that we are thinking about, but it's really more general about module systems. I've been programming large collections of theories and applications of categories and abstract relation algebra in Agda for the purpose of actual different unrelated code generation project. And here's just a tiny sort of fragment of that. I need a specification of category. A category is defined as consisting of a collection of objects, a collection of morphisms, and some other stuff. So if we turn this into a record, and record happens to be the standard way to do this in Agda, in ML this might be a module type, in Java this might be an interface, in Isabelle this might be a locale. It's the module mechanism that's the natural mechanism to use in this kind of context. So objects and homomorphisms are fields here. That is directly reflecting the usual mathematical definition. Or we could say a category over a given collection of objects with given way to provide homomorphisms consists of just the composition and the identity, and I've omitted the laws in both cases, turning the object collection, the homomorphism collection, into parameters. Which should I use? It turns out that in many cases a parameterized solution is appropriate. What I actually ended up using was just making the objects parameters, and this works wonderful for almost everything that I'm doing. But there is a question: what do you do as a library designer? Why do I do this, or why do I do the one that I'm doing? This is a question that not only I have run into. Tom Hales, the mathematician who solved the Kepler conjecture and who then found that his reviewers didn't believe his proofs, so he asked the machine instead to confirm his proofs. He looked into Lean, which is just another dependently typed programming language and theorem prover, after having collected lots of experience with Haskell-like, which is not dependently typed. And he finds that in Lean, people tend to meaninglessly parameterize structures from a mathematical perspective. And that's exactly the kind of parameterization that I showed on the previous slide. He goes on to explain that that this is somewhat similar to currying for functions, whether you have a function take a tuple of arguments or take the arguments one at a time. But there's a difference between currying functions and currying structures. For currying functions, you have uncurry. For currying structures, you don't. You mean what is bundled cannot later be opened up as a parameter in normal settings. And that's exactly what we are looking into. So summarizing this in a couple of words, it's about library design. And library design has, of course, the goals of reusability and generality. But if you are in a setting like Lean, like Agda, where you write, at least as part of what you're doing, mathematical theories, you also want to have some mathematical naturality of your exposition. And that really produces a conflict of interests. These two don't always go together very well. For a structure bundling up a couple of items, like a category bundles up a couple of items, collections, operations, and so on, there's the questions: which of these items should be parameters and which should be fields? of the structure. How do we do this? 4 simpler examples that we can look at more closely. Look at monoids, mathematical definition of monoid. A monoid is a set together with a binary operation and a designated element of that set where the binary operation is associative and that designated element is a left and right identity. This is the mathematical definition of monoid. We could instead make the carrier parameter and say a monoid over a carrier consists of operations and laws. And that's pretty precisely what an instance of the Haskell typeclass monoid is. So the Haskell typeclass monoid has explicit parameterization over a type, and that we can reflect in this approach. And that's used in many other places. But we can also imagine that we instead might want to parameterize by not just the carrier type, but also the operation. For example, if we want to talk about the additive monoid of integers, then not only the carrier is important integers. If I say tell you monoid of integers, you ask which monoid of the integers. We want the additive monoid of the integers. How do we do that in Haskell? We can't. At least not with the type classes in the way that the monoid type class that I mentioned works, because instances of Haskell type classes are indexed by types only. So for type bool, there can be only one monoid instance. And the solution that Haskell people adapt is that they can create isomorphic copies of a type using the new type mechanism, which have a different name. The type system works by name, so we can attach a different instance to one new type than to another. And that's what's used in Haskell to achieve parameter instantiation of what you want to make an operator a parameter in addition to a type, in the view that I presented for my monoid abstractions. So these are just some combinations of different fields that we might make parameters. Are these all we're going ever to need? How are we ever going to know that these are all we're ever going to need? We won't. So that tells me if I'm the library designer, I have to make everything a parameter. That makes a really ugly interface. It's not natural, and it's really ugly, and it's hard to use. So we go the other way around. We propose a solution that does not commit to anything being a parameter, but allows us to unbundle things at post, sort of as converse to instantiation in the same way that uncurry is converse to curry. And we call the new language feature that helps us achieving that a package former. So now we can do the definition of monoid as a package former. It looks exactly like it looked before, it just has a different keyword there. Okay, and then once we have a package former, we can use what we call variationals to recreate the different special cases. So the one we had in the beginning, we get that by invoking the variational record for our package former monoid P. We get exactly back that original record. If we want a parameter, we could do that in 2 different ways. We could either call the variational unbundled 1, or we could call the variational exposing carrier, and we get the one where the carrier is parameterized. Here I'm actually invoking the results that I produced on the previous slide with the record. So the monoid P record has also this name, so we can now also use that name and abbreviate our instantiation slightly. So we have this language of variationals, and we can go on to also do this for monoid 2 now in an even larger number of different ways, different but equivalent ways, and we get 2 parameters. So with all these instantiations, we have just 3 lines to get from each line what before was just as long as the whole definition. So it's linear in the number of instances, whereas if you program these manually, you tend to, if you do something that has about as many instances as you have items there, at least a quadratic effort connected with producing all the right interfaces that you might want to use. We can do more. We can, and I have encountered this need in my theory developments, also create term types automatically. The simple version is sort of useless, so this is the language of ground terms in the language of monoids. In some other theories, this is going to be more interesting. To make it useful for monoids, we have a variant that also allows us to produce an additional parameter for a set of variables that are then injected into the carrier of terms. So this is terms over monoid terms over variables, not only ground terms like this, without additional effort. So at least this one is something you can't get from a version that parameterized everything. All the others you could get with some effort from a version that parameterized everything. This one's really different. For this one, you have to duplicate this effort in probably essentially almost all programming languages that are around right now. So this is a new facility here that can be extremely useful in many contexts. I gave you by example the language of variations. So we really think of a variational as a function from package formers to package formers. We apply them postfix. We have function composition and identity for these, and we have those that you have seen that allow us to put together these combinations that create all the instances that we had previously manually derived. And we can extend this. If we add something like in Haskell you would call this default definition, so more items with a default definition, this is instantiated appropriately and types are derived for it. So if we take our old instantiations, this produces for each of these instantiations a corresponding instantiation of concatenation, which is mostly defined exactly like there, but the types are quite different, and the types are generated by our prototype system together with the instances that you have already seen. The prototype system that I mentioned is currently implemented as a editor tactic metaprogram. In the default IDE for Agda, which is Emacs. And even though I'm an extremist and I essentially only program in Haskell and in Agda, I haven't been quite able to convince Musa of that. So he's actually programming in eLisp and has been doing quite a lot of that. He put 5 meta primitives into this, and from that he derived all the things that I showed you. The meta primitives are much lower level, but they are Lisp. This then generates an Agda file, which is automatically imported into the current file. So this just meshes with the normal Agda workflow. You write the things that you want to do in the package former variation language in special purpose comments for Agda purposes, but then it generates Agda that's actual Agda that you don't have to look at, but that you can look at if you want, and it looks fairly normal. He has some more support for IDE, so he's highlighting the package formers just like Agda code. And if you hover over one of those instantiation invocations, then it gives you in the pop-up tooltip the code that's actually generated by that. This one is a new feature that I haven't shown so far, because you see the M set here is actually sort of a generalization of vector spaces, has 2 carrier sets, scalars and vectors, and operations between them. And then we massage that, we turn that, we apply a single sorted variational to it that merges the 2 sorts so that the only remaining multiplication now goes scalar to scalar to scalar, and puts everything together according to that. So that works. It's not all what we want to have done. If it was all, then I would be starting using that if I could find time to get back to my Agda stuff. This already could make my life much easier. But in the end, we really want a formal semantics for package formats and variationals that meshes with the Agda type theory. So that will mean that we need to refactor these meta primitives that currently carry a strong Lisp flavor into something more Agda type theory flavored, and integrate probably with a reflection interface for Agda. Agda had an old reflection interface that has been thrown away. It has a current reflection interface that is not powerful enough for the kinds of things we want to do. Perhaps it's going to be intended, perhaps there will be something new, but we really want to program this stuff in Agda, which corresponds to the fact that Agda can be used as its own meta language, just like Lean is its own meta language in one of the strengths that Tom Hales pointed out in the blog post that I referred to at the beginning. Then there are several different, more technical things that we're interested in looking at. Can we make sense of multiple default definitions, perhaps may make alternate sense for different variationals? What can we do in terms of inheritance, in terms of coercion, in terms of transport along canonical isomorphisms? From a program generation point of view, there are lots of low-hanging fruit. The challenge will more be to make this blend well with the type theoretic language itself. Another example is we can think about generating mutual definitions for certain variationals from package formats that have multiple carrier sets and things like that. What we already have is experimenting around with names and syntax and concrete syntax and combinator interfaces, and all that may change. So if you get a really good working version of that in 1 or 2 years, then perhaps everything looks drastically different. But the way it's right now, it already would allow me to drastically abbreviate many of the things that I'm doing in Agda. I have lots of use cases for many of the features that we have presented here. I just currently don't have the time to actually do any Agda. We already influenced the naming convention of some things in the standard library by Jacques posting a link to this paper on the standard library issue tracker and making some publicity for that. The main thing really is thinking this other way around about parameterization, to allow ex post parameterization, to allow unbundling, makes it possible to codify and name and document something that one could call as design patterns of using structuring mechanisms, using locales, using module types, using interfaces, and so on, and turn these into reusable entities that can be reused at a higher level. And this can in particular drastically reduce the size of the interface of libraries that mostly export other interfaces, module types, structures, and so on, and has on the whole the potential to drastically change how we provide and use structures via libraries. Structures like categories, like monoids, like many other things that you can think of, graphs, and so on. Thank you very much for the attention.
We have time for 1 or 2 questions while the next speaker is setting up.
Whether it's generative, uses named modules, or whether it goes by structure. And that's one of the many things that has not really been explored in the way it should have been. So we are right now exploring, looking at different use cases. I have brought up this question. It has not been dealt with yet.